Okay, welcome to another edition of Mr. Weis Solves an Old AP Problem. This time we're tackling the 2011 Calc BC exam problem number 4. And here's what the setup for this problem is. We are given a function f of x. We are given the graph of this function. We're told a couple of things about the graph of this function. So first of all, these two things are quarter circles. So this part right here is a quarter circle. This part right here is a quarter circle, and then it follows a line. And this is the graph of f of x. We're then defining another function, g of x, as partially an accumulation function for f, so telling us the area under f, but also with this other little business right here, this 2x. And so that's basically the setup of this problem. Part A asks us to compute three things. It wants us to find g of negative 3, g prime of x, and g prime of negative 3. So we have to find g of negative 3. Part A wants g of negative 3, g prime of x, and g prime of negative 3. So let's just tackle them one at a time. So g of negative 3, that's pretty easy. That's 2 times negative 3 plus the integral from 0 to negative 3 of f of t dt. To compute this, we're finding the area under f from 0 to negative 3. So note that we're going backwards. So if the area is above the x-axis, we'll consider it negative, and it's below the x-axis, we'll consider it positive, and it's the area under the curve. So going over here, here's 0 to negative 3. So basically, we're computing the area of this quarter circle right here. That's what we're being asked to find, is the area of that quarter circle. And that is a circle of radius 3 centered at the origin. So that's going to end up being negative 6 plus pi r squared divided by 4. So 9 pi over 4. And that would be my answer for the first part. Okay, for g prime of x, we're using here the fundamental theorem of calculus part 2 along with some other rules about derivatives. So here's like kind of a power rule. The derivative here is just 2 plus, so we're using a sum rule that tells us that the derivative of this can be just found as the derivative of the sum. This ends up equaling f of x. And so then g prime of negative 3 is pretty straightforward. It just simply asks us to compute what is 2 plus f of negative 3. So going over here to figure out what f of negative 3 is, this is f. Negative 3 right there, so it's 0. So this is 2 plus 0, which is 2. And so these, I suppose, are my final answers. And there you have it. Quick edit. Right after I got done saying that we're going backwards and so the area has to be negative, I forgot to include that. So it's actually negative 6 minus 9 pi over 4. We are tackling part B of the 2011 AP Calc BC exam number 4. We have the same setup as for part A. We have this function f of x defined by 2 quarter circles, then a straight line. And we have this function g of x, which is partially an accumulation function for f, but also has this little 2x bit. What part B is asking us to do is to find the absolute max of g on the interval from negative 4 to 3. So we're finding the absolute max of this function. So pretty straightforward. The way you find the absolute max of a function on a closed interval, a continuous function, which this is in fact a continuous function, it's the sum of two continuous functions, so it is continuous, is by finding all the critical numbers that are inside your interval and comparing them to what's going on at the endpoints. So here we go. First step then is to find the critical numbers. So g prime of x, we actually found already in the previous part, it equals to 2 plus f of x. And what we want to do is set this equal to 0 or does not exist. In this case, f of x is continuous on this interval. It's not differentiable though, but it's nice and continuous. A couple parts where it's not differentiable, by the way. I think here it's probably not differentiable and there. But it doesn't matter. We're not asking when it's differentiable. We're asking when it exists, and f of x does always exist. So the only issue is when this equals 0. So this occurs when f of x equals negative 2. And this is actually f of x that we're looking at here. So when does f of x equal negative 2? So we want to try to figure out where this is. That's where f of x equals negative 2. So you could go figure out where this is. I think it's pretty straightforward. I believe this is just a straight line that goes through the point 0, 3 and 3, negative 3. So it has a slope of negative down 3 over 1.5. So I believe this ends up happening here at 2.5. 2.5 or 5/2. To perfectly check this out, you could come up with the equation of this line, set it equal to negative 2. You should find out that it's at 5/2. You know what the slope of this line is. You know its y-intercept, in fact. So it's easy to come up with the equation. But you will find out that this happens at x equals 5/2. Okay, so now it's interesting. We have a couple options now. There's only one critical number in this domain, so we have a couple of options. Option number 1, we could go back and figure out what g of 5/2 is, figure out what g of negative 4 is, and figure out what g of 3 is, and we could see who's the winner. This is one option. One option. We could find g of negative 4, g of 5/2, and g of 3. We can literally compute all of those things and see if 5/2 is a winner. We have another option though. We're looking for an absolute max. There is a chance that this is a relative max. And since it's the only critical number in our domain, if this is a relative max, then it's also an absolute max, and we can be done because there's only one critical number in our domain. So that would be option 2. Option 2 is, if it's the case, I'm actually not sure, show that x equals 5/2 is a relative max. And we have a couple of options for doing that. We could use the first derivative test, or we could use the second derivative test, possibly, to figure out what's happening here. I'm going to do the second derivative test because I think it's a thing that a lot of people don't use. So let's try to do that actually. I'm gonna take option 2. I'm gonna hope it works out because, like I said, I don't know that this is the case. It's possible that the relative maxes could be at the endpoints. But let's see. So I'm going to find g double prime of x. So g double prime of x would just be f prime of x. So now I would just want to find g double prime of 5/2, which is f prime of 5/2, which is the slope of f at 5/2, which is clearly a negative number. Thus, by the second derivative test, x equals 5/2 gives a relative max. Since it is the only critical number, it gives an absolute max. And that completes the problem. Okay, here we are tackling part C of the 2011 AP Calc BC exam number 4. We're dealing with this function f of x defined by a graph over here. We've got two partial circles, quarter circles, connected with a line, and then we're defining g of x in this way. And for part C, we're asked to determine where g of x has any inflection points. Find inflection points of g of x. Okay, well that's pretty straightforward. An inflection point occurs at any place in the domain of the function where it changes concavity. So these are going to be any place in the domain of the function where the second derivative of the function changes sign. So that's what we're going to look for. So in order to do that, we're going to have to find g double prime of x. But I actually did that on the last board. And since g prime of x is 2 plus f of x, g double prime of x is actually just equal to f prime of x. So what we're asking ourselves are where f prime of x could possibly change sign. So that's what we're looking for. So I'm just going to go over at our graph here and we're going to see, is there any place where f prime of x changes sign? f prime of x, remember, is the slope of the tangent line to f. So here we are looking at f. It looks like we have a tangent line that's originally flat. It's increasing and positive, so the slope of the tangent line is more positive, more positive, more positive, more positive. It goes to infinity, but still positive, still positive, still positive, still positive, still positive. We get to here where it's flat, and then suddenly it changes to a negative slope. And then it's negative, 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 negative from then on. So the only place where f prime changes sign is at x equals 0. So f prime of x only changes sign at x equals 0. So x equals 0 is a point of inflection for g of x. And that's the answer to part C. Here we are tackling part D of the 2011 BC Calculus exam number 4. In part D, we are asked to look at this function. We're actually not going to use the g that we had been using previously. Here we're just going to look at the function f of x, defined by these two quarter circles and then a straight line. And it says to find the average value, the average rate of change. Find the average rate of change. This marker is dead. Find the average rate of change of f on the interval -4 to 3. So not to be confused with the average value of a function, which is what I said originally, but very common mistake. We just want the average rate of change. So that's easy. The average rate of change is literally just going to be f of 3 minus f of -4 over 3 minus -4. So let's see. F of 3 is -3. So we have -3 minus f of -4 is -1. All over 3 minus -4, which is 7. So we end up getting, it looks like, -2/7. By the way, -2/7 is the slope of this line that connects these 2 points. This is, after all, the average rate of change of this. So we just found out that the slope is -2/7. You can see it's a negative slope, makes some sense. Now the rest of part D says, why don't we have a contradiction to the mean value theorem here? Because there is something interesting. It turns out there is no point between -4 and 3 where the slope of the tangent line equals the slope of this blue line. And this is what the mean value theorem says must exist. This is what the mean value theorem says. The mean value theorem says that there is, for continuous and differentiable functions, there is always a place where the instantaneous rate of change equals the average rate of change. And in this case, that does not happen. But in this case, it does not contradict it because there is a place where f of x is not differentiable. So my answer to this is, this does not contradict MVT, since f of x is not differentiable on -4, 3. In particular, there's a discontinuity there's a location of non-differentiability at x equals 4.